Am I audible? Okay. I'll just share my screen. Hope my screen is visible, right? So, welcome all to the uh, sixth problem solving session for the course Geotechnical Engineering 1. Please switch off.
Sir, join
Uh,
oil.
so, uh, to start with, welcome all to the problem solving session of the sixth week of the course Geotechnical Engineering 1, and which is handled by Professor D.N. Singh from IIT Bombay. And I am Yogendra Narayanan. I am a PMRF research scholar. So I will be conducting these sessions. For these sessions are intended to make the learners proficient with the concepts that have been taught in a particular week by solving problems that have been that are similar that come under these concepts uh, to familiarize the uh, learners in order to facilitate them in attending these questions in NPTEL exams and and thereby it will be useful in further preparations for competitive exams as well as in their professional careers as well. So essentially, these sessions is to enhance the learner's understanding to apply the learned concepts in solving problems. So to give a brief uh, preview of what has been covered in this week is that mostly the concept of compaction, the techniques of compaction, both laboratory and field, and the procedure for obtaining dry density and optimum moisture content and their significance and on what factors do they depend upon and which are the factors affect these the compaction characteristics also. So it is a since it is a fairly uh, small topic which has been covered and mostly this as far as this compaction is concerned, it is more relevant in case of laboratory experiments more than in theoretical aspects. So as far as this session is considered, what we'll do is we will revisit some of the uh, problems in effective stresses and then transform and then translating this to compaction and we will see some practical examples or, or problems related to real life problems related to real life uh, numerical questions, maybe more uh, close to reality. How the compaction and dry density, optimum moisture content are obtained or applied in uh, actual engineering problems. That is what we will be seeing this week. So once again, welcome all. So I will be going to the first question of today's. So initial three, four questions will be on effective stresses. Since it is more critical concept required um, for further understanding of the concepts also. So I thought of giving it more. I thought of emphasizing it more so that you uh, you will be more familiar with once the concepts of seepage and consolidation are being introduced further in the courses. So, coming to the first question today. So, The question is, the water table is located at a depth of 3 meter below the ground surface in a deposit of sand 11-meter thick. The sand is saturated above the water table. The total unit weight of sand is 20 kilonewton per meter cube. Calculate the total pressure, pore pressure and effective pressures at depths 0, 3, 7 and 11 meter from ground surface and plot their distribution. So first of all, the basic approach for these problems for especially effective stresses and in future for consolidation application of problems related to consolidation. So the first step is to translate the question to a diagram. So first, uh, let this be the ground level, uh, and the dot deposit of now it is given that the deposit of sand is 11 meter. So let this be 11 meter and let this be let this be 3 meter where water table is there. Hope I'm audible, right? Mm. So if I'm not audible or if you are unable to see the slides, please let me know. So
Sir, font of the question slightly smaller, sir.
okay. Just a minute. Now it's fine.
Yes, sir. Better, sir. Now.
Yeah. Just a minute. Yeah. So the first option will be, am I audible now? So there was an issue with my mic and this one, so that's why I'm just confirming it. So because in recording it might have an issue. Is it audible? What I'm speaking? Yeah. Thank you. So as far as this is considered, so first approach is we have to translate the given question, given statement into a diagram. So the first step as far as this is, so let this be the ground level.
What is gamma W, sir?
You can take it as 10. If it is not specified, you can assume, as far as these sessions are considered, you can assume it as 10. But in examinations, either it will be specified as 9.81 or 10.
Okay,
If
sir.
it is not specified, you can take you can write the initial assumptions as this one and or you can assume it as 10. Mostly in exams, these issues will not be present mostly.
Okay, okay, sir.
So let this be the point of 11 meters. So as far as this question is considered, the water table is located at a depth of 3 meters. So this is 3 meters. Let this be 3 meter point. 3 meter. This is water table. This is 3 meter. All right. Now what we need is they have given and one more important point what they have mentioned in the question is that so obviously this part is completely saturated, that is below the water table. So here gamma sat is 20 kilonewton per meter cube. And one more information what they have given is the total unit weight of sand is 20 kilonewton per meter cube, and the sand is also saturated above the water table. That is, SR here is 100%. So the same gamma set can be used here also. So now we have to plot uh, total pressure, pore pressure, and effective stress at the depth 0 meters, 3 meters, 7 meters, and 11 meters. So let's just extend it. This is 0 meters. Let this be 5. Let this be 7. It is not up to the scale. So since my drawing is freehand diagram, so it is a little bit, it may be out of scale. So let's extend this. So first is total pressure. So this is 5 meter point. This is 7 meter points, right? So first is total pressure. Total pressure at 0 is, let this be the reference line. At 0 is, it is 0, right? Now coming to 3, total stress will be gamma sat is 20 into 3. It will be 60. So the unit is kPa, so that I need not repeat it. So here it will be at 5 meter, it will be 20 into 5.
Sir,
Yes.
at 5 meter, they didn't ask any questions, sir.
Okay, 7. Okay, then
You can remove that line.
yes. 3 and 7 was it, right? Okay.
Yes, sir. Okay, sir.
Yeah. So gamma sat is 20 kilonewton per meter cube. So let this be the reference line, and this will be applicable here. So now at 7 meters, it will be 20 into 7, which will be 140. So it will reach again to 140. And here it will be 20 into 11, which will be 220. It will reach again to 220. So this is the distribution of total stress with the values at 0. This is 0. Values at 0, 3, 7 and 11 meters. Now coming to pore water pressures. So pore water pressures at point 0 is 0, and it remains still here the water is saturated. but there will be no, the entire water here will be at atmospheric pressure. So we don't have any, uh, how to put it? So there is no mention of any capillary rise or something, or uh, so first case is, let there be the water is the layer is saturated, but they did not specify the reason whether it is due to capillary rise or not. So first case will be, let us solve only with without capillary rise, but the water is saturated, but hence this also will be at atmospheric condition. It will be 0. Now this is the water table, which makes this as phreatic line. So below the phreatic line, there will be hydrostatic pressure gradient. So that will be, now at 7 meters, it will be gamma W. Gamma W is 10. Let it be 10. 10 into 7, which is 70. And further, when we increase it at 11 meters, it will be,
Sir,
yes,
a small mistake, sir.
yeah, yeah.
It is 10 into 5, 10 into 4.
Yeah, yeah, okay, okay.
By
10 into
mistake, you
4.
have taken
Ah,
7.
yeah, yeah. 40.
40, sir.
Yeah, yeah. Thank you, thank you.
Welcome, sir.
And this is 3 to 11, it is 8. So this will be 80. This is the pore pressure distribution. Now coming to the effective stress distribution diagrams. So it is just total stress minus pore water pressures. So now what happens is, now here it will be 60. 60 minus 0, it will be 60 only again here. It will be 60. And here, at this point, that is at 7 meters, 140 minus 40 will give you 100. And here, 220 minus 80, that is, it will give you 140. This is 140 kilonewton per. The unit has already been mentioned. All right, any doubts? Any doubts?
No, sir. Fine.
So now let us extend this. So we have what I have done here is, initially we have not assumed any capillary rise. So now we will, since the saturation, now we will assume that the saturation above the ground, above the groundwater table is due to capillary rise. So now we can calculate the effective stress accordingly. So now this entire pore pressure will change, right? So now I will,
Sir,
yes,
you are using a PPT, na, sir?
yeah, I'm using PPT.
Then you can duplicate the slide, and in this only you can use a different color and modify the capillary problem.
Yeah, yeah, okay, okay. I'll just change my pen color. That also will do. Yeah.
Yeah.
Now, ah, so the capillary rise, if we consider capillary rise in this itself, so capillary rise is pore pressure due to capillary rise is UC, let it be UC is equal to minus gamma W into Hc. Since it is entirely saturated, then it denotes that the height of capillary rise is till the ground level, right? So now at this point it will be 0, and at this point it will be in negative. This will be minus 10 into 3, which is 30 kPa minus 30 kPa. Now in the case of effective stress diagrams, what will happen is that, so here 0 minus of minus 30 will be plus 30. It is plus 30, and it reaches here, it will be 60, and here it will be 100, and here it will be 140. 100, 60, and 30. So this is how the difference here between this is the difference which capillary rise causes in the effective stress on the soils. Understood? Any doubts, any clarifications, or any discussions? Right. So moving to the next question. So this is the question which we solved last week. So now I have introduced a surcharge load in this question to understand the effect of surcharge on effective stresses. Right. So the same question, a layer of clay extends from ground level up to a depth of 6 meters. I think is the font is right, or shall I make it a bit bigger? Or one thing I can do
But
is,
it is better if you make, now it is very clear, sir.
right.
Yes, sir, very clear.
So the layer of clay extends from ground level up to a depth of 6 meters and overlays a 6-meter thick sand layer. The water table is at 6 meters below the ground level. The unit weights of saturated sand and unsaturated clay layer are 20 kilonewton per meter cube and 16 kilonewton per meter cube respectively. A surcharge load of 15 kilonewton per meter square is acting on the ground level for a long duration. Determine the following, and they have given some parameters that needs to be computed. So same thing, let us translate this statement into a diagram. So a layer of clay extends from the ground level up to a depth of 6 meters and overlays a 6-meter thick sand layer. So let this be ground level, and this is, let this be 6 meters, and this is the water table. Let this be sand deposit, sand, clay, 0, minus 6, minus 12. I'm just writing the level, or if it is confusing, let me just write it as 6 meters, 12 meters. Alright. So second is saturated sand is 20 kilonewton per meter cube. Unsaturated clay is, this is, let us consider it as dry. There is no, or whatever saturation, partial saturation is there. So there is no any capillary rise or something. So it is just it is existing in its natural state. So 16 kilonewton per meter cube. And major difference what we had is the surcharge that is acting on the ground surface. which is 50 kilonewton per meter square. So before solving this, so since there are some new uh, who are undergraduates who might first it is important to understand what is surcharge load. So how do you define surcharge load? How do we exactly define surcharge load?
I think it is a temporary load due to the equipments
Yeah, that is
or
fine. No,
accumulation of the ice.
yeah, that is uh, these examples which you are giving is the uh, real life applications. So if we consider the loading pattern, how a surcharge load will be acting. So the surcharge load can be in case of since you are aware of this preloading and all, so that is also a surcharge. So, but what is the nature of this load? One is it is fairly uniformly distributed load. And what about its extent? And what is the assumptions that we make regarding surcharge load?
I think it is extended to the infinite in both direction.
Yeah, it is a semi-infinite load, a semi-infinite uniformly distributed load. So here, uh, see the extent of this is we know the magnitude of load which is acting, which is 50 kilonewton per meter square, and it is the domain which we are considering it in both the dimensions. It is we assume it to be of infinite extent. So both into the plane as well as across the plane. So that is the major assumption. Surcharge is defined as the load that is acting on a soil uh, soil layer, which is of which induces a that not induces which covers the infinite extent both in at least in one direction. So uh, now the first question, coming to the first question, effective stress at 3 meter below the ground level. So we have defined the problem by we have pictorially depicted the problem. So now it is time to solve the given questions, compute the given parameters. So first requirement is effective stress at 3 meter below the ground level. So how to do it? So here there is no pore water pressure. So first is so question A, total stress. So here straight away we can write since U is 0, sigma is equal to sigma dash. Now how to calculate sigma is the surcharge load which is already a stress. So at every depth, whichever depth you are calculating, it will remain the same. So that is how it is considered. So that in this case it will be at a depth of 3 meters, also it will be 50 only. So you should not multiply it with depth like you do in uh, for pore water pressures and uh, total stresses. So that is the uh, point that you should take care of it while solving the problem. So 50, which is due to surcharge, plus the remaining is due to the clay layer that is present over the considered point, which gives us 16 into 3. So this is the first point. Let this be some point A, which is 3 meters. 16 into 3, which is 48 plus 50, which gives us 98 kilonewton per meters square. Now coming to point B, pore water pressure at 6 meter below the ground level. Since 6 meter is the phreatic line, so pore water pressure will be 0. Q is 0. Coming to the third question, total stress at 6 meters below the ground level. So that is, it's fairly simple. 50 plus 16 into 6. This is 50 plus 96, which is 146 kilopascal. Right? Now coming to the question D. Pore water pressure at 12 meter below the ground level. So pore water pressure starts at 6 meters. So the water column is 6 meters. So UW at 12 meters is gamma W into H, which is gamma W, you can take it as 10 into 6, which is 60 kilopascal. Right? Now coming to the last question, effective stress at 12 meter below the ground level. So effective stress at 12 meters, sigma dash at 12 meters. So please bear with me. So there is a shortage of space. So I am writing above. So if you are unable to follow, let me know. So total stress should be calculated first, which is 50 plus 16 into 6. This is for clay. This is for surcharge. This is for clay plus 20 into 6. This is for sand. This is the total stress. Minus pore pressure is gamma W is 10 into this point is 60 into 6. So how much we are getting? 96, 146. We'll get 206, I think, right? 146 plus 120.
Yes, sir.
So it will come 266 minus 60, which is 106 kilopascal.
206, sir.
Sorry, 206. So if you remember in last week, we got an answer of around 156 to 158. So due to the effect of surcharge in this case, what is happening is that effective stress, the difference in effective stress with and without surcharge is that the difference is the surcharge load only. So this is also one of the uh, interesting observations which we get by in understanding the effect of surcharge. Some important observations which we got are: so when reducing the water table, the effective stress acting at a point increases. That is one of the important observations. Second one is, if there is no change in effective stress when there is a change in water level above the water table. So if we have a lake above the bed, or a river, the depth of the river above the river bed does not matter as far as effective stress are considered. The change in levels of the river or lake, whatever the water body is present. So that is one of the important observations. And third observation is the difference in effective stress between with surcharge and without surcharge is the surcharge load only. So this I have demonstrated in this case, because if you come across any type of question similar to this, you can directly, if it is an objective type question or you need a uh, quicker answer, then you can directly use this observations as the in order to solve the problem. Any doubts, any clarifications, or any discussions?
Yes, sir. Just now I updated this last point which you have mentioned, with surcharge, without surcharge.
Yeah,
With surcharge, we have solved the answer. Effective stress at 12 meter is 206 kPa.
yeah,
Same question I have done it just now. Without
uh,
surcharge, effective stress is 156 kPa.
yeah.
Therefore, difference is exactly surcharge.
Exactly,
So,
the surcharge. So that
surcharge.
is what we are through this question we are trying to understand, and I was trying to demonstrate it.
Yes, sir.
Okay.
I updated this point today.
Yeah, yeah.
Thank you, sir. Thank you.
So moving to the next question. So this is one of the interesting questions. So I think we will enjoy solving this question. So the surface of a saturated clay deposit is located permanently below a body of water, and the laboratory tests have indicated that the average natural water content of the clay is 47%, and the specific gravity of soil solids is 2.74. The first question is, what is the vertical effective stress at a depth of 10.5 meters below the top of clay layer? That is the first question. Furthermore, an excavation is made by dredging and by keeping the water level unchanged. What depth of clay must be removed to reduce the effective stress at the same point by 50 kilopascal? So let us solve this question one by one. So first, let us list down the parameters known. Yeah,
Sorry, sir.
yeah, yeah,
Sir, can I ask a small extension before starting this example in the previous example?
yeah, yeah. Please,
Can you go back to the previous slide, sir?
just a minute. Yeah,
Sir, your conclusion
yeah,
with surcharge, without surcharge, difference is nothing but a surcharge only,
yeah,
corresponding to effective stress at 12 meter.
yeah,
Now my question is, the effective stress at any depth, including ground level or 6 meter at 12 meter, anywhere, the answer is same, no?
yeah. It will be same.
Even on the ground also, easiest way,
Yeah, one of the best ways to verify that is take
ground
at the
level.
ground level.
Yeah, because effective stress and total stress both are same. It is 50 only on the
Yeah,
ground.
50.
If you remove the
This,
surcharge, it is zero.
yeah,
Effective stress is zero.
yeah, yeah.
So difference is 50 only.
Exactly. So
Okay.
this result is ideal for effective stress only.
Okay.
So uh, only way you can verify it is take at ground level. You will get ground level also. This surcharge will be 50,
Okay.
and by removing the surcharge, it will be 0. So
0.
the difference is 50, obviously.
Yes, sir. Thank you, sir. Now we can proceed.
So moving to the coming back to the question here. So the surface of a saturated clay deposit is located per. Okay, I have read the question. So let us try to understand the question step by step. So first, let us translate the question to diagram. Surface of saturated clay deposit is located permanently below a body of water. So first is the water table, or this is water level, and this is the ground level. And what they have done is water content here is 47 percentage, and specific gravity is 2.74. So which is ideal for a clay. So now what they have done, what we have done is we have translated it. Now here we don't know the H. Let us see if it is actually required or not. Now coming the depth at which the point of our interest is, let it be point A, and it is at 10.5 meters, right? So now what they are asking is, what is the vertical effective stress at a depth of 10.5 meters below the top of clay layer? So this is what they are asking. Now we have to compute sigma dash, which is sigma minus u, which gives us sigma is, let gamma w be 10 kilonewton per meter cube. Now this 10 into h. First, for initially we have to compute gamma sat. So let us come back again to this point. So we need gamma sat. So since it is completely saturated, we can directly compute gamma sat, which is gamma w g into 1 plus w divided by 1 plus wg, since s is equal to 1. Yes, sir. All right. So what we are getting here, we have water content, we have specific gravity, we can calculate it. 10 into 2.74 into 1 plus 0.47 will give you 1.47 divided by 1 plus 0.47 into 2.74. How much we are getting? Gamma sat 10 into 2.74 into 1.47 divided by 1 plus 0.47. Approximately 17.61. 61 kilonewton per meter cube. Are you getting this?
Yes, sir, it's correct.
Yeah. So now we can calculate the effective stresses at depth of 10 meters. So it will be sigma dash is equal to sigma minus u, which gives us sigma is first is let 10 into h plus 10 into h plus 20. Sorry, it was in the previous question. So 17.61 into 10.5. This will be the total stress minus pore water pressure will be 10 into h plus 10 into 10.5. So now 10 into h and 10 into h will get cancelled. So how much we will get here? 17.61 into 10 point is. Now what we know here is now it is 17.61 minus 10 into 10.5, which gives us 7.61 into 10.5. So what is this 7.61?
Submerged unit weights.
This is submerged unit weight. So when you get more proficient with the calculation of effective stresses, so if somebody is asking at a particular point to calculate effective stress, and the water table is completely that is the entire column is under water table, then you can directly multiply effective stress as gamma submerged into the required height. So now how much we get? We are getting 10.5 into 7.61. We will get 79.9
89. Okay.
kilopascal, right? Here we are again demonstrating that the level of water column above the ground level does not matter in effective stresses. All right. So this is getting cancelled here. All right. Now this is the first part of the question. So second part is now what people are asking is, furthermore, an excavation is made by dredging and by keeping the water level unchanged. So the water level is unchanged and some dredging is happening. Right. So if I change the color here, so it is some excavation is occurring to some depth, right? But there is no water column. So let this be some this is occurring. So what depth of clay, and due to the dredging, what happens is that the effective stresses is getting reduced by 50 kilopascal at this point at A. So for this condition to occur, what depth of this clay must be removed? All right. So that is what the question is. So we need to calculate D. All right. So how to calculate it? First, we need to understand what is the difference in effective stresses. So initial effective stresses that is otherwise we can write as sigma dash I, which is 79.9 kilopascal, and sigma final is, it has to reduce by 50. So 79.9 minus 50, it is 29.9 kilopascal. All right. So in order to get this value of 29.9 kilopascal, what should be the depth? So we have 10.5 here. So 29.9 is equal to, as I told before, now we are concerned only about effective stress. So directly gamma submerged can be used into 10.5 minus D. Is this step clear? Any doubts?
Sir,
Yeah.
you are finding the D now,
Yeah, yeah,
not
yeah.
not below the D.
No, no, we are finding D.
Then directly you can write gamma submerged into D.
No, no, here
Okay,
what
okay.
is, yeah,
Yes, yes, sir.
so
Yes, sir.
after submerged, so to make it clear, so now we are removing this, right?
Okay, okay,
Now the remaining soil will be about this only.
okay,
So for that it will be 10.5 minus D. So
okay,
the
sir.
contribution of effective stress, which results in the contribution of the soil above it to the resultant of 29.9 kilopascal is this much.
Okay, okay.
So now you know gamma submerged, which is 29.9 is equal to, gamma submerged will be 7.61 into 10.5 minus D. Alright. So now if we calculate 29.9 divided by 7.61 will give 3.93. So D will be 10.5 minus 3.93, which will give value of around 6.58 meters, which is D. Understood? So in order to get an effective stress of 29.9 kilopascal at the tower point of interest, that is point A, the amount of soil that has to be dredged is that is the amount of depth for which the soil has to be dredged is 6.58 meters. So that is what. So this example is to give another dimension for the application of effective stresses. Any doubts here, especially in the second part? So first part is fairly straightforward. Second part, as far as second part is concerned, yeah,
Yeah, yes, sir. It's clear. Good example.
yeah. So I think with this our effective stress part comes to an end. So if I come across any interesting problems, we will solve then and there in further weeks also. So because this This will be, if you are entering into geotech, so this will be your lifelong acquaintance. Okay. Now, coming to this question, calculate the maximum dry unit weight of a soil mass having a Voigt's ratio of 0.7 and G is 2.65. The optimum moisture content is 17%. So it is a fairly simple problem. So gamma dry max, this will be according to zero Arrowhead's line. Let us consider this at zero Arrowhead's line to start with. So gamma W G just a minute, just a minute. So first let us calculate the saturated unit weight, gamma bulk. Both ways you can do, I think.
Sir, without moisture content directly, you can use the formula, sir. Gamma
Yeah,
dry is equal.
that also can be done.
Yes, sir.
Yeah. Just try to solve this and let me know what the answer is.
Option D, sir, 15.6.
Yeah, so it is a fairly straightforward. That's why I did not do it. So to just for an sake of clarity, since it will be in public forum, so I'm just doing it. Gamma D is equal to gamma WG by gamma D is equal to gamma WG by 1 plus E. So this is the formula which you need to use. Alright. So now this corresponds to zero Arrowhead's line, right?
No, sir. It is
It
a
is for,
maximum dry density. Gamma D a max. As
yeah.
per the
So
question, gamma D max means there will be some voids there.
yeah, it
Okay.
will be, no. Here the voids are there, which corresponds to voids ratio of 0.7. So here the major assumption what we do here is the dry density. Obviously, the saturation will be zero. That is what the assumption is here. Uh, and yeah, fine. 15.6.
50.6.
Now, coming to the next question. In a standard Proctor test, the weight of hammer, that is, it is not a standard Proctor test, but in a Proctor or a compaction test. Let me just reframe this question. A standard Proctor is fixed specifications. In a compaction test, right? In a compaction test, the weight of hammer considered is 3 kg instead of 2.6 kg, and the number of compactions layers are 5 instead of 3. So what will be the new compaction energy transferred to the soil? So now for this we need to understand uh, how the energy is calculated, right? Sorry. So For this, we need to understand how the energy is calculated. So now it is based on simple conservation of energy. So how we do it is, if we consider a soil sample is kept, you are filling it, and a hammer is there. It is lifted to a height, particular height. So height here is not changing. So it, and it has a mass or weight, which corresponds to uh, this is, now it is 3 kg. Let it be m, and this is h. Now this hammer, when it is falling, so it has a, not when it is falling, at this position has a potential energy of mgh, right? And this energy is converting into the compaction energy on the soil for each blows and for each layers. So in as far as modification from, that is the alterations from standard Proctor test is, hammer weight m is 3 kgs, right? G is 9.81, 9.8 meter square per second. H will be 31 centimeters, which is 0.31 meters. And number of layers n is 5 layers, right? Now the energy, total energy imparted is m g h into, and number of layers is 5, and number of blows, let it be nl, and nb is 25, right? mgh into nl into nb, right? Now it will be 3 into 9.8 into h is 0.31 into nl is 5 into 25. How much we are getting?
What about volume, sir? You are cancelling both sides?
Yeah, and that is, we are giving per meter cube, right? So the volume will be 1000,
Okay.
not 1000. It will be
1000 cc.
yeah, 1000 cc. So that has to be converted to meter cubes. So first let us calculate this energy for uh, entire thing. So how much we are getting?
1140.
Yeah. So 1140. I think 1 meter cube.
Yeah, both the sides, it's okay, sir.
Yeah, yeah. So it
1140,
is
yeah.
both side the volume will get cancelled. So it will be 1140 kilojoule per meter cube. Right. And one more thing is, the 1000 meter cube is 1000 liters is 1 meter cube, right?
Yes, sir.
So this will give you, see, since it is this all are in SI units, right? So see, this has to give us uh, how much? It has to give us 1140 joule per liter, right? Because uh, the volume of this compaction mold is liters. So if you convert it into meter cube, it has to be 10 power minus 3 meter cube, which when we take it up to the numerator, it will become 1040 kilojoules per meter cube. That is how this options were there. Understood? This is just a
Yes.
unit conversion. Now let us move to the next question. Out of the following methodologies, which one is used for compacting coarse grained soils? Out of the following methodologies, which one of the following is used for compacting coarse grained soil?
Vibrations.
So it will be vibrations. So sheep foot flow rollers are most useful for clays. Even static compaction is used for in as far as some laboratory conditions are considered, static compaction is preferred. And falling weights can be that also is used mostly for clays for uh, but essentially falling weights is dynamic compaction. So that also vibrations is large scale vibrations involve blasting and uh, major. One of the best example is blasting, which gives a uh, vibrational loads at a very small interval of time. So, as far as coarse grained soils are considered, vibration is the best um, technique for compaction. Select the desired objectives of compaction. So, increasing of shear strength, decreasing permeability, decreasing settlement, all of the above.
D, sir. All of the above.
So, just for a clarity, so when we are doing compaction, to let us consider at the desired objective of compaction, that is, we need to achieve gamma d max, right? So when at gamma d max, that is at maximum dry density, with uh, the shear strength will increase, which is essentially due to the more packing of decrease in voids ratio, more grain to grain contact, and uh, these two. And since the voids ratio is decreasing with increase in gamma d, there will be an increase in decrease in permeability. And since shear strength is increasing, its stiffness also will increase. So for a particular stress, the amount of deformation that is undergone by the soil is reduced. So that is why it also facilitates in decreasing the settlement. So all the three options are right. So these are the objectives of compaction.
Sir,
Yeah,
excuse me, sir.
yeah, yeah,
Decreasing the settlement means it is immediate settlement only, right, sir?
yeah.
Okay.
Yeah. So prolonged settlement, it does not
Not,
depend on
yeah,
uh,
compaction.
compaction.
Yes, sir.
So that is then it is consolidation, time dependent settlement is.
Okay.
And also, as far as compaction is considered, it is only removal of air voids, right? So obviously, it will be immediate settlement. So now, so here we are having four parameters, which is optimum moisture content and gamma dry max. sorry, here you can write maximum dry density, max. Maximum dry density and optimum moisture content for standard Proctor test and modified Proctor test. Now, what will be the correct relation between these parameters? So for this, we need to understand the compaction characteristics curve. So this will be gamma D. This will be water content. And first, the standard, let us consider standard Proctor test. We let this be the response. And this is WOMC for Proctor. This is gamma D max for Proctor. Now, coming to the modified Proctor test, it will be the energy imparted to the soil will be higher. So, for minimum number of blows, or for the not minimum number of blows, if the total energy is since the total energy is higher, the soil is capable of attaining even more higher maximum dry density at a lesser moisture content, optimum moisture content. So, for modified Proctor, the compaction curve tends to shift in a slightly upwards and towards left. So this will be WOMC modified Proctor. This will be gamma D max modified Proctor. Now, if we consider this magnitude, so WOMC of Proctor is greater than WOMC of modified Proctor. So this option is not right. Sorry. So this option is not right and this option is not right. Now coming to that gamma dry max. Gamma D max of Proctor less than gamma D max of modified Proctor, right? So in this case, gamma dry Proctor greater than, so this is the option. So this is not the option. This is the right option. Provided both the soils are same. So if the soils are different, then its characteristics also will be different. Coming to the next question, match the following. So it might be a bit confusing. So this is the condition, and these two are the attributes of this condition. All right. So first is dry of optimum. Second is wet of optimum. So first of all, we need to the second column specifies in real life condition where it is preferred, and the third column specifies what is the behavior at deformation behavior at several at different types of stresses. All right. So here dry of optimum dry of optimum, since its permeability will be higher, it will, and it is it is more suitable for the outer part of the embankment or the dam itself. So then A will be corresponding to J, and wet of optimum, its permeability will be very low. So it is preferred for the core of the dam. So B will be I. All right. So this is fairly straightforward. Now coming to the deformation behavior. So we need to understand how these two, dry of optimum and wet of optimum, behaves at low stresses and higher stresses. All right. So now for that we need to understand the compression curves. So deformation, how can we measure deformation? Simple parameter is,
Void ratio.
yeah. So it will be Voigt's ratio E, and stresses will be effective stresses. Now here it is normal effective stress. Right. Now at lower stresses, the ideal behavior will be, let both dry of optimum and wet of optimum. This will be the deformation behavior of dry of optimum. This will be the deformation behavior of wet of optimum. This is wet. This is dry at lower stresses. Right. So now with increase in stress, or the ideal understanding is that the less deformation is, let this be initial E, and at particular stress, let this be ED, EI, and this is EW. Right. Now deformation is, it is of 2. For dry it will be EI minus ED and EI minus EW. Right. Now which will be higher? So this is delta E W, and this is delta E D. Now delta E W is greater than delta E D. So deformation of wet of optimum is more. So now dry of optimum preferred for embankment, less deformation at low stresses. So the option is A, J, and X. Now coming to the higher stresses, this will be the ideal behavior. E sigma dash. So this will be for dry, and this will be for wet, wet, dry. Alright. Now this will be, let, if we consider this slope, since here there is a reason why, is have you any idea why here both the values are starting from a single value, and here it is not? Any idea?
No, sir. For me,
Yeah.
no idea.
So let me just, if I extend this, all right. So this is at lower stresses. This is at time t equal to 0. And if you go at a very high stress, in this case around 100 k 1000 kPa. So there are some reference books ideally at which these values are given as 1000 uh, uh, th- uh, how to put it, 1000 kPa, 1200 kPa. So it this uh, this part of the graph is just an extension to this, right? So ideally it will result in a equal void ratio. So that is how this is. So initially we are considering lower stress values and higher stress values. So in this case, its slope, dry slope is more than wet. Dry of optimum slope is more than wet of optimum. Hence, wet of optimum has lesser deformation at higher stresses. So this is how, based on several applications and the amount of load that is getting that is estimated to act on a particular earthen structures. So whether to go for wet of optimum or dry of optimum is getting decided. Hope it is clear. So here it will be
Sir,
EI. Yeah,
the first part of the graph is clear because you have taken EI, ED, and E vector.
yeah, yeah, yeah.
You have explained.
Mm-hmm.
But the second graph you have not taken. Where is
Yeah,
the EI
here,
for second graph?
because see, that is what I have tried to explain. What is it is
You,
that,
you can change the color of the pen and
yeah,
write for
yeah,
the second
just
case.
so this you are able to see the graph for higher stresses, right? The top graph, this one. This is the graph for higher stresses. Now this is nothing but just an extension here. So this is some, let us, when the stress is getting on increased at a very high stress, it tends to behave like this. So when we consider this higher stress portions only, so the slope, uh, here we cannot, since it is not at equal initial voids ratio, here one of the most ideal way is to compare the slope. So here the rate of change of void ratio is lesser compared to that of dry. So this is dry and this is wet. It is just a continuation of the graphs. Clear?
Okay, sir.
Yeah.
Sir, what is the source of this particular graph, sir? You have referred?
Yeah, yeah. These are ideal graphs. You can refer Lambda-Whitman.
Lambda and Whitman. Okay,
Yeah.
fine, sir. Thank you.
So in that they have clearly responded. Or you can also refer Gopal Ranjan and ASR Rao.
Okay. Okay,
So
sir.
and because in Lambda-Whitman, the ideal values for this stresses where this changeover occurs will be quantified. To the best of my knowledge, I have seen somewhere.
Yes, sir.
So
But Indian authors, I have not seen any textbook.
yeah, this it will be available in Gopal Ranjan, but this concept will be available, but not with numerical values.
Uh, okay, sir. I will
Yeah.
check it.
So coming to the next question, what will happen to the capillarity if the soil is compacted? If the soil is compacted more, this is a slightly misleading uh, question. Compacted more is towards, let us consider ideally it is at gamma D max. Right? Initially from some lesser density to gamma D max. In that case, what is happening? What happens?
Increases.
It is increasing. Why it is increasing?
Voids are
Because
reducing.
voids ratio is decreasing. So we know that Hc is indirectly dependent on E into d time, right? So since E is decreasing, Hc tends to increase. That is how this is done, right? Now coming to the next question. A soil sample compacted according to the standard Proctor test has a density of 2.06 gram per cc at 100% compaction and at OMC of 14%. What is the dry unit weight? And second question is, what will be the dry unit weight at zero air voids line? Corresponding to zero air voids. If voids become filled with water, what would be the saturated unit weight? Excuse me. Hello? Am I audible?
Yes, sir.
Uh, can you just wait for some 5 minutes? I will be back.
Sure, sir. Thank you.
Yeah. Sorry.
Yeah, it's okay, sir. Go ahead.
Yeah. Am I audible now?
Yes, sir.
Yeah. So
What is the 100% on the last line, sir?
yeah, yeah. So here at 100% compaction is that is it is referring to gamma d max. That is whatever this is the bulk density corresponding to peak. How to put it? Maximum compaction density, right? So gamma bulk is 2.06 gram per cc. And now water content is 14%. Now gamma D max is gamma bulk minus by 1 plus W, which is 2.06 divided by 1.14. How much we are getting?
18.1.
Yeah. So 18.1.
Kilonewton per meter cube. I got it. Otherwise, 1.81 gram per cc.
You are multiplying it with okay 10 na?
Yeah.
1.81 gram per cc,
Cc.
right? Now second point is what is the dry unit weight that is considered, that is over. This is done. What will be the dry unit weight at 0 air voids? So that will be gamma D is equal to gamma W G divided by 1 plus WG. So we'll be getting 1 into 2.67 divided by 1 plus 0.14 into 2.67. How much you are getting?
1.94.
Yeah. So 1.94 gram per cc. So now these two are done, right? Now whatever the bulk density which we have got initially at max, that is maximum dry density, that that is in unsaturated condition, right?
Yes, sir.
So if that voids is again filled with water, so such that for the same maximum dry density, if you are saturating the sample, so what will be the attained saturated unit weight, and that is what it is that is what me is being asked here, right? So here the one of the simple ways to approach this will be the consider the total volume as 1 cc, right? So in that case what we'll do is we need to calculate, so saturated unit weight. So
Sir, is the answer is not exactly same as 1.94 for the next case also?
no, it will not be same.
Because at
This is dry density.
1.94, at yes, sir, at 1.94,
uh,
the percentage of air voids is zero. Indirectly, degree of saturation is 100%.
yes, that corresponds to dry density.
Yes, sir.
So if you convert this to uh, uh, saturated unit weight,
Okay.
uh,
Water
you
content you have to multiply.
you will get a fairly higher value. So and it
Okay.
also it cannot be attained. You know that. right?
Okay.
So since
Okay.
compaction
Okay.
curve does not touch the zero air voids line,
Okay.
so that's why we take this one. For this only, they are asking what will be the saturated unit weight for at this dry density.
Means void ratio minimum is same.
Yeah, yeah, yeah.
Okay, sir. Okay.
Void ratio will be same.
Yeah.
So now we need to uh, uh, calculate the saturated unit weight, which is gamma sat is total weight by volume. Volume we are taking it as 1 cc. So hence it will be total volume, which is weight of solids plus weight of voids, which should be equal to weight of water, right? So now you know dry density gamma d is equal to weight of solids by total volume. So weight of solids will be 1.81 grams per cc. So volume is per cc. So weight of solids is 1.81. Now second is we know the water content. So water content is defined as weight of water by weight of solids. So weight of water will be how much? 1.81 into 0.14, right? So this is 0.253 grams. That is present here. So now we know what is the weight here, weight of solids and weight of water that is already present. But the main thing is we don't know what is the total weight, total voids, or how much voids, how much of total voids is there such that the weight of the water content is 14%. So for that, what we can do is we know gamma solid, which is weight of solid by volume of solid, right? So volume of solid will be weight of solids is 1.81. Gamma solids will be gamma W into G. So which will give us 1.81 divided by 2.67. It will give 0.68 cc. Now since total volume is 1, volume of voids will be 0.68, 1 minus 0.68, which will give us 0.32 cc. If we convert this to weight, so that is this entire thing is getting occupied by water. So this volume, if we convert it to weight, weight of water will be total final. This is initial, will be 0.32 grams. So now we know the total weight is 1.81 plus 0.32 grams per 1 cc. So in that way you will get 2.13 approximately. So this is the saturated weight density, unit weight that you will be getting. So if you want to calculate amount of water that is getting added, you can calculate weight of water final minus weight of water initial. In that way you will get 0.06 something, 07. This is 2.253, it will be 0.067 grams. Any doubts? So the question might seem bit small,
Yeah.
but it has a very good application of concepts.
Sir, this gamma set last part,
Yeah, yeah.
this is the gamma set at OMC. Yes, sir, no, sir?
Yes, exactly.
For
Yes.
compaction curve.
Yes, yes, yes.
Then is it possible to use directly formula? Gamma set is equal to G plus E by 1 plus E into gamma W, in which E is equal to E minimum.
But we don't know. We cannot get here. That also can be done because you have.
Yes, sir, I have done it. I got the same answer, 2.11. Because
Yeah, yeah.
rho d max is known to you.
Yes.
Then if you use the formula G gamma W by 1 plus E minimum in that
Yes, yes.
formula,
That also you can do. Yes.
uh, I got it. It's the same answer almost.
Yeah, yeah, yeah. That also can be done.
Okay, sir. Done.
So this will give you how
Yeah, fundamentals, principle from
yes, yes. Crisp
principles we got this.
fundamentals. Exactly.
Yeah.
So that is why I chose this approach. So
Okay, sir. Done.
because it will come from first principles, right? So how it goes into, you can understand how several phases are distributed. So that also
Yeah.
can be revisited briefly. So
This
the
question
build,
is actually third part.
yeah, yeah.
Really, it is not possible, no, sir. On compaction curve, saturation is not possible. Only for understanding purpose.
Yes, yes, yes. Actually, one thing what can be done is when you are conducting triaxial test, right?
Hmm.
So at the time, initially you'll be preparing, if you consider you are preparing a sample corresponding to uh,
Rho
OMC
max.
and MDD,
Yes, sir.
and then you will be saturating it.
Back pressure.
Yeah, when by applying back pressure. In that
Hmm.
case, it might be it,
Applicable.
because you will be measuring simultaneously Skempton's parameter also.
Yes, sir.
So in that case, it might come handy, but not in real life.
Yes, sir. Yes. Thank you.
So a bell-shaped Proctor compaction curve implies which kind of grading for a given soil. So this bell-shaped Proctor compaction is a qualitative depiction. So ideal compaction curve, sorry, compaction curve gamma d and W bell-shaped is something like this. So this will ideally we will get it for well-graded soil. So this is not ideally we will not get a this kind of typical curves. It is very rare phenomena that we get this. So but ideal conditions is that it should have a clear cut bell type of curve for a well graded soil. All right. These are fairly small questions, so there are some questions which we can uh, do it. Yeah. So which grain structure of soil is prevalent on the wet side of compaction curve? Which is the
Dispersal.
dispersed. So these are direct from the lecture. If you have gone through the lecture, or if you are uh, some mostly it is covered in lecture also, I think. So coming to the next part, the ratio of energy imparted to the soil in standard Proctor and that of modified Proctor is. So for that we need to understand the specifications of standard Proctor and modified Proctor test. So we know that energy is M G H N L into N B per some volume, right? So For standard Proctor, volume remains same, so we can ignore this standard and modified. So the only ratio is this one, E standard by E modified will be M is for standard Proctor mass of the hammer, which will be 2.6 kgs. G is 9.8. H is 31.31 into layer is 3 layers, blows is 25 blows. Right. Now coming to the modified Proctor, weight will be 4.9, 9.8 into height of fall will be 0.45 into 5 layers of 25 blows each. So this will be cancelled. So how much we are getting? 2.6 into 0.31 into 3 divided by 4.9 into 0.45 into 5. You will be getting around 0.219. This is the ratio. So actually one more reason is that why we are not considering volume is that you have any idea why usually in compaction energy
Mold is the same, na, sir.
mold is same, that is one thing. If we are converting this Proctor, right, so this mold to any, you are scaling up or scaling down the molds, all right. So in that case, usually the apart from this total energy, the governing parameter will be total energy per volume.
Okay.
So to have a same effect, now let me give a situation here. So you have a standard Proctor test, all right, okay, and
Yes.
what you are going to do is you are constructing a similar uh, you are constructing a new device for compaction with the lesser dimensions.
Okay.
All right, now the
Volume also changes.
volume also changes. Now the major thing is, the major condition is that that is the major objective of this is you need to impart same amount of uh, compaction effect. You need to you need to get a same compaction effect in both the cases. Then how can you decide these parameters? How can we decide these specifications? So that is where we need to take into account energy per unit volume.
Okay.
So if for the both cases you have energy per unit volume same, then you can play with the dimensions of the dimensions of the mold as well as number of blows and everything.
Okay.
So that is how, if you are going to see now there are many miniature compaction apparatus that are available. So if you take that, it will be like a small toy. So it will be around uh, it will be the entire compaction setup it will be for a comparison, it will be like a triaxial sample only.
Okay.
So in that case also you can get this same effect that is getting imparted on standard Proctor test is by comparing the uh, energy per unit volume. So that is how we have to scale it. So now Moving to the next question. The maximum and minimum dry densities of a sand were determined in the laboratory to be 1682 and 1510 kilogram per meter cube respectively. In the field, the relative density of the same sand is 70%. What is its relative compaction and dry density? So we know relative density 70%. That is, you can write as 0.7 equal to 1 by gamma d minimum minus 1 by gamma d divided by 1 by gamma d minimum minus 1 by gamma d max. Right? So now we will get what is the gamma d achieved in field. So 1 by gamma d minimum is 1510 minus 1 by gamma d divided by 1 by 1510 minus 1 by 1682. Right? Now how much we are getting? 1 divided by 1510 0.7 is equal to, you can take some thousands out and cancel it. So 1 divided by 1.51, you get 0.66 minus 1 by gamma d divided by 0.66 minus, this will be into 1000. Plus 1 divided by 1.682, 0.59. Now if you subtract this, so get 0.0455 equal to 0.66 minus 1 by gamma d into 1000. Now let us take this here, 1 by gamma d equal to 0.66 minus 0.0455. It will be taking 1000 common. Sorry, it will be 1000 here.
You get 1626.
Yeah. So ideally it will be 0.61 divided by 1000. Same 1 divided by 0.0006. How much you are getting?
1626.
Yeah. So it will be 1. So the entire gamma D will be 1626 kilogram per meter cube. All right.
Yes, sir.
Now we need to
C.
relative compaction. So relative compaction is density obtained maximum density obtained in field divided by density obtained maximum. So it will be 1626 divided by
82.
1682. And it will come around
96.7.
yeah. So that is the maximum limit which can be achieved also when we translate laboratory studies field. So you have been practicing, right? So have you come across any situations like this?
Yes, sir. In theoretical, some books also I studied RC also possible more than 100 also.
Yeah, that is possible. In
Yeah.
this case, because there are some sands in offshore sands, right?
Okay.
So in that case, there is a possibility of RD relative density itself exceeding 100%.
Oh, RD itself, sir.
Yeah. So some Norwegian sands exhibit this.
Okay, okay.
So it was taught to us in MTech. So some
Mm-hmm.
Norwegian sands uh, tend to show this effect.
Okay. I thought of only RC will exceed, but RD also will exceed.
RD also there are some peculiar cases where it can exceed.
Okay, okay.
So that is 96%. And for bulk density you need to calculate gamma bulk is equal to gamma D into 1 plus W.
What?
So gamma D is 1626 into 1 plus it is
Point one two.
directly write as 1.12. We'll get as 1626 into 1.12, which is
1822.
double. 1822 kilogram per meter cube. So with this we'll stop today. So there is one more problem which is an interesting problem. So which due to shortage of time we will be carrying over this problem to next week. So thank you for attending this session. Hope it was useful. So these sessions are scheduled at on every Saturdays from 5 p.m. to 7 p.m. I encourage all the NPTEL learners to attend and get benefited. And uh, if people attend, so there is there are more possibilities for generating good discussions. So, hope to uh, looking forward to see you next week. Thank you.
Thank you, sir.